Good day again, dear participants of the Congress. How is work? The first week is already coming to an end, but this is not scary since there is still a lot of interesting things ahead. We are starting our traditional excursion. This time they will be held in an unusual format, like the Congress itself. We hope you will enjoy it and it will be informative enough. Today, the excursions will take place in the laboratories of the Tomsk Polytechnic University, and next week we will conduct the same online excursions to several laboratories of our institute, namely the Institute of High Current Electronics. Today, you will visit two laboratories which the guides themselves will tell you about. The total duration of the tour will be about 1 hour. You can also ask questions in the chat. I think we shouldn't wait long. So for the first excursion, I invite on the air our first guide, and I see he. This is Roman Cherepanov. Roman, when you are done with your tour, just pass the word on the next tour guide. Okay? You have a floor, please. Roman?
Good evening.
Okay.
Do you hear me?
Yes, we hear you.
Well,
We
I'm
hear
ready to
and see you. Start, please.
I'll try to open
Demonstrate your. Yes.
where I'm stopped. Do you see my presentation?
Yes, we hear you and see you.
Well, let's
Very
try
well.
it again. My name is Roman Cherepanov. I present National Research Tomsk Polytechnic University. And my laboratory is the Laboratory of Modern Manufacturing Technologies. It's a short attempt to make my presentation. We start from plastic printing section. This is our room. And here you can see our main equipment, high temperature printing machine. This machine allows us to work with high temperature plastics and with conventional PVA, ABS, PCR, and other consumers plastic, but also it's worked with PEEK and other high temperature plastic. One of important features of this machine is direct introduction of reinforcement fibers to the printing area. And we can add fiberglass, we can use aramid reinforcement fibers, and we can use carbon reinforcement fibers to print reinforced parts and details. It's our milling CNC controlled machine. We use it for some metal parts and for service functions. Here we have high temperature box for plastic preparation and a small milling machine for shredding of used plastics to reuse of materials. Small flying box And our students have lab works with consumers 3D printers, Upbox, and two other printers. I can't remember their names. Also, we have Gotek Pendulum impact tester for investigation of strength properties of plastic materials, which we obtain with our printing machine and investigate their properties. The next our room contain equipment for metal working. First of all, it's a robotic ultrasound tomography complex for non-destructive testing of printed material, printed parts, printed details with minimum size of defects. It can carry out around 100 micrometers and scanning speed up to 1 meter per second. It's our laser machine for selective laser melting. This machine uses ytterbium fiber laser with maximum power of around 1/2 of kilowatts and working area about 10 centimeters in each direction. This machine works with atmosphere of air, nitrogen, and with the atmosphere of inert gases and other gases, as well as in vacuum experiments can be carried. The second machine is electron beam melting machine, which is equipped with electron beam source with thermal cathode. Accelerating voltage for the electron source is up to 60 kilovolts, and the power of the source is up to 4 kilowatts. Machine can be equipped with powder melting module and with unit for wire melting and for printing with metal wires. It is also possible to use this machine for welding of parts with complicated geometry. Maximum working area for this machine is around 10 millimeters in each direction, but we have also units to extend this area to size around 20 centimeters in X and Y direction and around 15 centimeters in Z direction. Also, we use some testing equipment for investigation of material properties such as elastic modulus, elastic limits, shear modulus, and other elastic constants, and to obtain sigma epsilon diagrams for materials, as for printed plastic materials and for printed metal materials that we can get from our printing machines. This is a replacement part for our electron beam source. We have our own electron beam sources with electron beam sources which we developed and manufactured in our laboratory. Well, that's all about our equipment, and I think this is the end of our excursion. I can answer your question if you have. Any questions?
Dear participants, if you have any questions, you can write them in the chat. We should wait. Okay. Yes, we have one question. Can you use any powder in electron beam surfacing system?
No, electron beam matching works in vacuum, and therefore we can use only powders with electrical conduction. We use titanium alloys, we use steel alloys, and aluminum alloys is possible to use in our machine. But in general, any electrical conducting powder we can use. If we use wires, there is no problems with conduction because wire is electrically conducting always, and we can use any wire.
Okay. And Amir Valiyev, could you tell please about real projects which you realized?
Some research programs under our scientific organization. Now we conduct one project under fundings from Russian Scientific Foundation. This project is about melting of titanium powders and about modeling of melting and sintering process of titanium powders. This project is not finished yet, and we in progress. We also use our laser matching for investigation of biocompatible niobium titanium alloys and investigate properties of biocompatible mixtures of titanium and niobium. As for plastic machines, we have some contracts with our motor building companies and medical application with Siberian Medical Institute. One of the projects was about printing of model of child's hearts for assisting heart surgery in Siberian medical organizations. Surgery staff use printed models of hearts, obtain it with computer tomography and print it in our machine for planning of real operations in health organizations.
Okay. I have a question. Maybe I don't understand, but how far are you from a specific practical implementation? About your practical implementation.
It's very wide area. We use our equipment for welding of some parts for external orders. We have some scientific project about investigation of properties of printing process, and we use our electron beam matching and selective laser melting matching to develop scientific programs for measurement of properties of metals under high temperature, for investigation of surface effects near welding baths and near melting cooling, and for investigation properties of real powders from our Russian suppliers of titanium powder and suppliers of niobium powder. We use our equipment for produce some parts for medical usage, and
Okay.
that's all.
Yeah. Okay, thank you. Dear participants, do you have any questions? Thank you for your very interesting excursion.
Thank you, John.
Yes, and dear participants,
Now
if you have no questions, then we move on the next room. And our next guide is Yegorov. Ivan. Okay. Do you hear?
Yes, very well. What about me?
Okay. Yes, we hear you but don't see.
You all right?
We can see. Yes. Please start.
Shall I start? Yes, okay. Hello, everyone. I'm Ivan Yegorov from Tomsk Polytechnic University. And today I will tell you about few locations in our university in the laboratory of beam and plasma technologies. The first position is an ion accelerator, well known as TEMP4M. You can see it here, I hope. The accelerator parameters are accelerating voltage from 250 to 300 kilovolts. The pulse duration 150 nanoseconds. The ion beam density on the target from 50 to 250 amperes per square centimeter. And the ion beam consists of different charge carbon ions and protons. The construction is based on the traditional scheme, Bloom line scheme, double forming line, but with a feature. The feature is the additional gas gap in the charging circuit of a forming line, which make it possible to produce two pulses of different polarity. The first pulse, if you use it in ion mode, the first pulse will be negative for plasma production, and the second one will be positive for ion acceleration. This is a forming line. Main or general commutator is here, is a gas gap. The diode is here. So this accelerator also can be used in electron beam mode. about applications. You can see some of them here, like coating deposition and hard alloy treatment for improving of the cutting properties of the instrumentation. You can see the processes here. All of them simultaneously at the same time can be produced inside the vacuum chamber of the accelerator, and also you can see the room where the accelerator is located. You can find it physically in the room 01, building 11G, address Lenin Avenue 2A in Tomsk. Please visit us to find this accelerator. For the composition, the charging model is behind the accelerator, and the operator room is located near the accelerator too. The diode have a vacuum system based on diffusion pump, traditional for our equipment for this age. Okay, and after that, I think I will move to another position in the same building. The second position will be Electron accelerator, located in the same building in the room number 06.
Ivan, excuse me.
Yes.
We have questions from Alexei.
Connected with this one.
Yes. Other carbon and hydrogen ions can be used in the ion accelerator. You can see this question in the chat.
Yeah, I see it. Other carbon and hydrogen ions can be used in the ion accelerator, or it is possible to use other ions. It depends on the anode material. So if you want to know a little deep, please send us the email or maybe through the organization. Please ask the question to get the answer deeper, because of I just show you the positions, and more professional answers will be prepared by another guys.
Okay.
Okay. I will continue.
Yes, next, please.
Another position is the electron accelerator with a circuit based on pulse transformer. The transformer-based scheme make it available to produce very compact accelerator. You can see the high voltage part here. The dimensions for the accelerators is very compact, like 1 meter to 2 meters and close to 2 meters tallness. You can see it here. And this accelerator was produced for repetitive generation of the electron beam and output it into the atmosphere for some applications. You can see the room where there are a lot of additional equipment for testing of different applications of electron beams for sterilization, for surface sterilization, for some chemical reactions, and so on. The electron beam is directed from top to bottom, and you can produce different reactions inside the reaction chamber. I hope that this guide will be available online, so later you can find this information in additional. Okay, this accelerator has two steps for energy compression. The first step is also located in this installation. All of equipment located in one installation. From the semiconductor power source, we produce the charging pulses for high voltage energy bank. And you can see the scheme here. Sorry again. After that, the commutated energy will be loaded to the pulse transformer and to the vacuum electron diode fluid. There, the electron beam will be accelerated and then output to the atmosphere for some applications. Also, you can install the radiation shielding made of lead for better safety of the operator, and you can produce close to 40 or 50 pulses per second for continuous operation. One of the application is water treatment. You can see the results for water treatment analysis. There, some of purifications can be cleaned, can be treated, and you can see the details for disinfection. For such type of accelerator, one of the main application, as we see, is use it like a disinfection station for different low volume productions, like a cubic meter per hour, very low. Also, you can see in this room different parts of the accelerator. Is an old one.
You have a phone near to you.
Sorry, please. Can you hear me?
You have a phone. You have a phone near to you.
You mean sound?
Telephone рядом. Take it further.
What about right now?
Take your phone.
No
further.
phone. No phone. I don't know.
Phone?
Yes.
Okay. We have problems with our sounds.
I don't know, because nothing changed.
Okay.
Okay, I will continue. Also, you can see some details, some parts of the accelerator around. Is an old one or new one. We try to test it in this installation to improve the parameters. And also, we try in this laboratory to produce some equipment, diagnostic equipment, to know parameters of electron beam well. Something like this. Sorry, okay. Or something like this. If you turn around, you will see the operator room. Operator room is here, and the operator room is shielded by the lid inside the walls. there you can see the control panel. It has touchscreen display, and you can control the accelerator using this. Okay. If you will find this presentation online, also you can find the short video to demonstrate it, very simple experiments with our accelerator. Like water treatment, it is made by a student, but it is a very, how to say, you can see the process in details. Okay, let's continue. This room is used for testing and assembling different details of accelerator to produce some new equipment. And also we have office upstairs here. So maybe you will visit us, but please contact us before. And now I will give some words for my colleague. We will change the location also in this building, but another type of equipment.
Ivan.
Okay, I will return.
Maybe we have questions.
Okay, sorry.
We should wait, and if it's possible, I answer you. I have a question.
Okay.
What can you say about the average power of the electron accelerator and the resource of its cathode?
Thank you for questions. For average power, for this machine, it is available close to 200 watt of a beam in atmosphere.
Average power, yeah?
Yes, average power. If we're talking about the pulse power is close to 20 megawatts. Is a pulse power. And sorry, I forgot about the parameters of the accelerator. Accelerator can produce the pulses of electron beam with the accelerating voltage up to 500 kilovolts, and the voltage pulse duration is a half of is a half microsecond at full width, half maximum. And the current duration is close to 150 nanoseconds. And the amplitude is the current, okay, the total diode current amplitude is up to 1 kiloamp, and the output current a little low, close to 400 amps.
Okay, thank you. And what can you say about resource?
About resource. For this scheme of accelerator, for generator resource for today is more than 10 to 8 what we tested. I mean the resource of a generator. About the cathode, we have different types of cathode used for different operation modes. For long-term operation, we use graphite fiber cathode. For today, the resource for continuous operation is close to 10 to 6 pulses of electron beam. But right now, we have different research to study the cathodes based of liquid emission into the accelerating gap. So I think a little later we will tell you about this.
Okay.
The proposed resource of such type of cathodes for us is much higher because of the material for beam production will be the diet will be supplied by material for electron beam production, for plasma production.
Okay. Thank you. And I have one more question.
Yes,
how
please.
do you measure the average beam power?
There are two ways. The first way is we can measure different pulses. I mean the single pulses from the series of the pulses, and then multiply to number of the pulses. I mean the number of. Okay, we have the power for one pulse, and we can multiply it to the pulse repetition rate. And the next one we can use calorimeter for this.
Okay. Okay. And we have no questions. That's why we move to the next room. Yes?
Let's go.
Yeah, thank you very much for a very interesting excursion.
Please visit us.
Okay, thank you. And next guide is Maxim Serebrennikov.
No.
Am I right? Am I
Sorry?
right? No.
No. I think he introduced himself.
Okay.
We will start the presentation right now.
Okay, good evening, everyone. Can you hear me?
Yes, we
Okay.
hear you, but we can see you.
Okay, if you need, I will. Yeah, thank you. Hello, everyone. My name is Sergey Zenkin. I want to show you the second part of our laboratory, which is focused on thin film productions. And here you can see the first part of our group. Let's see. Here we have we use two different processes focused on focused on Pvd and Cvd techniques. In Pvd techniques, we mostly used magnetron sputtering. Here you can see it. Is it okay? It doesn't work. Yeah, okay. We construct this magnetron system by ourselves in our laboratory. Mostly we use it as for the production of a small experimental thin films like metals or some nitride coatings and so on. And here you can see that it can be it's very flexible and can be used for production of metals, oxides, carbides, and so on. It has installed substrate heater up to 1000 degrees C, oil-free vacuum system based on turbomolecular pump. Also, we have an ion source for the cleaning substrates before the deposition, and some system of rotation and movement of the substrates. Another system which we use, they are based on a CVD, so it's let's say dissociation of the working gas by the use of plasma or hot filament. So we have several systems, like use it as you can see here. it's used for the production of the uniform flat diamond by the dissociation of the methane and of the mixed gas of methane and hydrogen. So the second one has just a different configuration, but with the same technique. It's a hot filament CVD for the diamond production. And the last one, yeah, it's a system of the plasma enhanced CVD. We use a abnormal glow discharge for the deposition of diamond with a relatively high speed, up to 15 microns per hour. Also, this system allows us to produce a different structure of the diamond, like nanocrystalline, polycrystalline, and now we're working on the production of monocrystalline diamond synthesis. The deposition area for this method is up to 30 square centimeters. Also, it can be used for the production of the uniform and quite thick diamond coatings on the flat substrates and on the curved substrates, like for cutting tools applications and so on. So I think here we finished, and now we will move to another laboratory.
Okay, please, dear colleagues.
Just a second. I will finish with the second one, and then if you will have a questions, please ask.
But anybody has questions now?
Which one? I don't see. Phone making really? Oh no. Which one? Are the carbon and hydrogen ions used in the ion accelerator? Usually, we don't use carbon and hydrogen. If we
no.
It's another question.
Sorry for ion accelerator.
It's about yeah.
12 questions.
Okay, we can start, right?
Yes.
Yeah, with
Let's
another
continue.
laboratory. Yeah. Okay. Here is another.
But we have question now.
Do you experience with the effectiveness of your cutting tool somehow? Yeah. If we are talking about the effectiveness of coatings, it means that on which material we use cutting tools. Because, for example, if we are talking about the airspace nanocomposites, like carbon-based nanocomposites, the only one cutting tool which can work with these nanocomposites, it's diamond-coated cutting tools. And now we are working with several groups which are testing our diamond for the applications of for the cutting applications. Okay.
Okay.
Yeah. So here is another system which constructing also in our laboratory. It's like a semi-industrial system. Yeah, thank you for the question. It's a semi-industrial system, also worked with magnetrons pattern. but a little bit higher higher dimensions if you compare with the previous one. Also here we have two dual magnetrons, ion source for cleaning, also turbomolecular pumping, and here it's worked with several groups of nanocomposite coatings which we are focused on. It's hard coatings with low coefficient of frictions. It's metalloid nitrides based coatings like nanocrystalline metal nitride in a silicon nitride matrix. It's max phases based on a titanium aluminum carbide and titanium silicon carbide. And also we start now working with high entropy oxides, nitrides and carbides. Usually it's like from 4 to 6 equally mixed components, mostly focused on thermal barrier applications. The second one, yeah, so our magnetrons equipped, usually we equip it by the, how would say, mid-frequency magnetrons, but now we start to use high PIMS magnetrons also, so high power impulse magnetron sputtering. The second one is equal to the first one, but just use a different configuration of magnetrons. So here they are square one, and the second system is a circle. But other parts is absolutely the same, and this system is mostly used for the solid oxide fuel cells productions, for direct oxidation of the hydrogen. We use a thin electrolyte based on yttrium-stabilized zirconia. And also we have a supported anode, which we use as a support, and then deposit on it solid electrolyte. And also we now start working with a cathode, which is quite complex, but yeah. And the thickness of the cathode, electrolyte is relatively small, less than 5 microns. If you will compare it with the standard techniques, it's like 100 of microns and so on. So yeah, here's one of the benefits of use of magnetron sputtering, because we can produce very dense and high quality films with a very low thickness. Yeah, so if you have any questions, please ask me. No?
No, we have no questions.
Okay.
But nevertheless, thank you very much for a very interesting excursion. Very short and interesting excursion.
we are open for the discussion, so you easily can find us, and maybe for some cooperation.
Yes, okay.
Yeah.
Okay, thanks again.
Okay, thank you. Yeah, fine.
Goodbye. And dear colleagues, in principle I was right, and the tour took us about 1 hour. Now the tour has come to the end, but next week we will do, and we will inform you about the time of its holding a little later. Before the end of our meeting, I would like to remind everyone about poster presentations. They are all posted on the forum. You can get to know them and ask your questions. And now, thank you again. Goodbye.